Welcome back. So today is day 2 of week 4. So we were discussing about the properties of the characters of square matrices, and we said that for conjugate matrices we had identical characters. So we proved that point, and today I am going to show you a real example of that. So now if you concentrate on this here, this matrix represents the C3 symmetry operation. So C3 means just C3, and this matrix represents C3 2, that means operates C3 twice. So we know when we discussed about that ammonia problem quite some time back, we said that C3 and C3 square, they form a class. That means C3 and C3 are conjugate elements of that group. So now the matrix representations of C3 and C3 square, which are given here, they should also follow their own follow the characteristics of the symmetry operations. That means this 2 also should form a class. Therefore, these two matrices should be conjugate. If that is true, and if whatever we learned in the last class, if it is true, then their characters should be identical. Let's have a look at this. So the character is the sum of this diagonal element, right? So in this way, so minus half plus 1. What that means, that the character for this one is 0. Character is given by this chi. Now here again, if we look at this minus half 1, again the chi is 0. So that proves our point that conjugate matrices have identical character. Let's have a look at some more. So for the same problem of C3V, I have 3 sigma V's, and we also said at that point of time that these 3 sigmas, they form a class. Therefore, this matrix says representing this sigma V prime and sigma V double prime, they are conjugate to each other. Therefore, their characters should be identical. Let's verify that. So here the character is minus 1 plus 1 plus 1 means 1. Here minus half plus 1 means character is again 1. Here same. So again we have proved the point that conjugate matrices, which represents the conjugate symmetry operations, they have identical characters. Okay. So therefore we can see the importance of the character. If you think carefully, when we say that some particular symmetry operations belonging to a particular group form a class, so there must be something similar in them, okay, in certain properties, and that those properties should be also reflected by the matrix representations and thereby the characters as per the definition. Now we obtain the conjugate elements of a group by similarity transformation. Similarly, I can use the similarity transformation on their matrix representations to find the conjugate matrices. Now the characters of these matrices, which represents the symmetry operations belonging to a particular class, and we know that there is something similar in this symmetry operations, that is exactly reflected here when we look at their characters. All their characters are identical. So we used to say that there is some similarity in this symmetry operations belonging to a class, and we see here that their characters are exactly same. Okay. So that is an important lesson that you should take. Now very often we are dealing with combining symmetry operations and thereby combining matrices when we are talking about matrix representations. And we said that matrix representation can be very large. We can have like n by n can be like 30, 40, 50, 60, whatever numbers. Now if we want to combine two such matrices, it's really cumbersome. Now, there are ways to reduce our workload here. How? We can have the square matrices such that all the non-zero elements of those matrices are kind of blocked as a square block along the diagonal, and rest of the of diagonal elements are 0. Such matrices are called block factored matrix or block diagonal matrix. So on your screen you can see such example of block factored matrix or block diagonal matrices. So say this is matrix 1, this is matrix 2, and you can see that this square block along this diagonal, again this square block, they are all along diagonal, and only these blocks have non-zero elements, and this part or this part, they are all zeros. Okay, so this is one block factor matrix, this is another one, and they are block factored in the very same way. Okay, so that's what we have right now. Now, if we want to combine these two matrices, that means if we want to have the product of these two matrices which are block diagonalized, then we find this matrix, which is I say matrix 3. Okay, so what are the things that are important to find in this case? So the main important thing is that the resultant matrix that we get is blocked out or block factored in exactly the same way as the constituent matrices here. Okay, so that is very obvious. Moreover, the element of the given block, okay, we have 3 blocks there. So element of the given block in the product matrix are determined only by the elements in the corresponding blocks in the factors. Thus, when two matrices which are blocked out along the diagonal in the same way are to be multiplied, the corresponding blocks in each may be considered independently of the remaining blocks in each. So what does that mean? I have an overall matrix. Suppose I have 1, 2 and 3 blocks in the matrix, rest of the elements are 0, and I have another matrix of this which is block factored in the same way, and if I want to multiply them, I do not need to consider anything else. So I choose the first block here, do the multiplication, and you put it in the same block in another third matrix. You do the same thing for the second block, multiply with the second block of this matrix, third block here, and then put the resultants in their respective place in another matrix. So thereby you will get the matrix multiplication. So exactly that's what is shown here in this range. So you just multiply each blocks and get the overall multiplication or overall product. So suppose we have a group and we have its matrix representations, and matrices are like E, A, B, C and so on. Okay, and that represents a group. Now if I do similarity transformation on each of these matrices, we can find any matrix within the group which we will use for the similarity transformation. So that is what is shown here. Say like I find a matrix D and use that to do the similarity transformation on each of the elements of this group. Here it is each of the matrices. So I do a similarity operation on the matrix E, on matrix A, on matrix B and so on, and I get a matrix out of it. So I call it E prime, A prime, B prime and so on. Now this new set of matrices that I get by doing the similarity transformation will also form a representation. Why so? It is very easy to prove. So let me do that real quick. say I have two elements A and B, and I do the similarity transformation like using this matrix D. Now suppose I have a matrix A and matrix B such that A and B, if I combine, gives D. Okay. Suppose I have this condition. So say now I find I use this D to do the similarity transformation on on this product. Okay. So if A and B are two matrices and D is another matrix. Now if I do say a similarity transformation as D inverse A D equals to A prime, as we have just shown in the on your screen, and D inverse B D is B prime, and we want to show that this A B, they are part of this group that we are considering, and all these matrices A B C, all this forming a representation, and we want to show that upon this similarity transformation we are finding these new matrices A prime, B prime, C prime and so on. They also altogether form a representation of the group. Okay. So now if we combine A prime and B prime in the same fashion, okay, A prime and B prime, I will get something like D prime. I should get. So now if I do a similarity transformation on this product, okay, so what is A prime B prime? So A prime B prime is D inverse A D and D inverse B D, right? That is my D prime. So this one I can rewrite as D inverse, so maybe I should write it here so that you can see. So D inverse A D, D inverse B T. So this part is identity. So therefore I can write this is equals to D inverse A B D. Fine. Which means I have D inverse D D. So that means this is the similarity transformation of D. What I get is D prime, correct? So thereby I can see that this D prime, which is the newly formed matrix after the similarity transformation, can also act as the representation. Okay, so that's what is is written here. Now, having said that, if we suppose that when we are doing the similarity transformation on this matrices A, B, C and all, the new matrices A prime, B prime, C prime, they are that we are getting, they are block factored, and they are block factored in the same way. All of them are block factored in the same way. Then we are talking about some situation like this. So this A prime is the similarity transformation by this particular matrix D, and this is block factor in this fashion. So I have, say for example, here 4 blocks: A1 prime, A2 prime, A3 prime, A4 prime, and all the other matrices that are generated, say for example B prime or C prime and F prime, so on, they will be also block factored in the same way. Now, in that case, what we can have, we can again combine this newly formed matrices in very easily. How? Because we have just seen that block factored matrices which are block factored in the same way, we have to just consider each individual blocks and then multiply this with the corresponding block in another matrix. So here, if I have to find the matrix form of D prime, then I just have to multiply this blocks A1 prime and B1 prime, we get D1 prime, and we can get the other blocks also in the same way. So I get this newly formed representations in terms of like A prime or B prime or C prime, all these things, they form the representation of group. We just saw that. Now once we see that it is possible to take a representation like A, B, C that we started with, and then by doing some similarity transformation, if possible, we can block factor all these matrices, and those also act as the representation of the group. Then we can take each blocks and form a representation. So for example, this E1 prime, A1 prime, B1 prime, they are just the blocks taken out from each of these matrices that are formed out of similarity transformation. So another block is E2 prime, A2 prime, B2 prime, so on, E3 prime, B3 prime, A3 prime, so on. So each of this this set of this blocks are also the representations. When we can do these things, then we say this original representation that we formed, that is matrices A, E, A, B, and so on, they are reducible representation, meaning that I can reduce them into smaller blocks, smaller dimensions. I started with say 9 by 9 matrices for each representation, and I can do the similarity transformation. I can get say 3 by 3, 2 by 2, and 1 by 1 matrices, which themselves form the representation. Then the original representation that I formed is called a reducible representation. Okay, and on the other hand, if it is not possible to find a similarity transformation which will reduce the matrices of a given representation, the representation is called irreducible representation, or in short IR. We will be using this term very often henceforth, that's irreducible representation, or in short IR. Now just like the characters, this irreducible representation, they contain a lot of information, and they can be actually used for the practical application purposes. Okay, so we will see that in greater detail probably in the following class or next to next, when we learn about a particular theory called great orthogonality theorem. We will know how to deal with this irreducible representation, what are their properties, and we will learn about how these irreducible representations, they actually represents say any given molecular state, okay, or in other words the wave functions of any particular given state of the molecule. So those things we will start discussing in in the next class or the next to next. Now, after learning about the character, we will just mention to you about a table called character table, which is extremely important to us. So what is a character table? Obviously it is a table which is a two-dimensional table whose rows corresponds to irreducible group representations or simply irreducible representations, and the columns correspond to the conjugate classes of the group elements. The entries consist of characters, the trace of the matrices representing group elements of the columns class in the given rows group representation. So let's have a look at that particular table, which is known as character table, and that's on your screen. So this is the so-called character table of one particular point group. So essentially this particular tables tells us a lot about this about the symmetry of the particular molecule which belongs to this particular point group C3P here. Okay, so a quick look at this table will tell you that okay, there are several areas, several sections in this table. At the very beginning you can see the top left corner, you have the symbol of the point group, which is given by the Sohnfleisch notations. Okay, and then next to that you have the symmetry elements which are clubbed in classes. Okay, and then we have the characters, then we have certain other symbols, and some functions, linear or non-linear functions are there in different areas, which we have classified as area 1, area 2, area 3, area 4, and so on. So we will talk about this detailed divisions of the character tables, and we will learn those things in a bit greater detail. So first place, the area 1. Okay, so what does area 1 give me? So let's have a look at the area 1. So here we have all the characters given here. Okay, so each row, this row or this row or this row, they give me the characters of irreducible representations, different irreducible representation. We can see here that there are 3 rows, so that means we have 3 irreducible representations. So any character table deals with irreducible representation, it does not deal with reducible representation. Okay, that you must be very clear about. And this number of rows, that is the number of IRs that are possible for a particular point group, is fixed. Okay, so by doing an exhaustive analysis, people have already figured out that these are the numbers of irreducible representation that is possible, that is which is maximum possible irreducible representation for that particular point group. And you consult any standard textbook of group theory or symmetry, you will find this character tables there, or even you can get it in many books of quantum mechanics. Now we will talk about this different irreducible representations and all these things in greater detail when we will come to the great orthogonality theorem. Now that's about area 1. Now let's look at the area 2. So area 2, it contains several symbols. So earlier when we were forming the representation of group, we said that okay, the name of the representation of group is gamma. Okay, so we used the term gamma instead of this thing, so we said gamma, and we found that okay, those representations are probably reducible, may not be reducible, may be irreducible, but if we have more than one representation, so we used to differentiate by gamma 1, gamma 2, gamma 3. So that's like a generalized term. Here we can see there are some specific terms like A1, A2, E, and if you go to many other character tables for many other point groups, you will see there are various different terms. So like A prime, B prime, A1, A2, AG, EG, BG, and all those things, AU. So what are these terms that are written in area 2? So these are the symbols which is called Mulliken symbol, named after R.S. Mulliken. Now, these symbols are not given arbitrarily. There is a definite convention of using this particular symbols. So, let us see what are the particular rules or convention that are followed to do this nomenclature. So, when we look at any irreducible representation in the character table, we can find out their dimensionality. So, dimensionality of any irreducible representation is the number or the character corresponding to the identity operation, that is the dimensionality. Okay. So, for example, if I just quickly look back, so here I see that for the first representation we have the character as 1 for identity operation. For the irreducible representation, the second irreducible representation also has a character 1 corresponding to identity operation, while the third irreducible representation has character 2 corresponding to identity. So, the first two are one dimensional irreducible representation, while the third one is a two dimensional representation. So, we have to see what are the relations between different irreducible representation, their dimensionalities or there are certain other aspects, and how can we form, how can we name them by using Mulliken symbol. So, all the one dimensional representations, they are given the symbols as A or B. So, if you find an irreducible representation which has a character as 1 for identity operation, then you know that this particular irreducible representation will be either A type or B type. Okay. So, any irreducible representation which has a dimension 2, then that is termed as E, while irreducible representation having dimension 3 will be termed as P, okay, as it is written here. Now, after assigning this A or B or T or E for this particular IR based on their dimensionality, we move a little further. So, let us see what are those. For one dimensional irreducible representations, after we have assigned that they will be either A or B, how do we know whether it will be A or B? We have to look at the character correspond to the principal axis of symmetry. If the character corresponding to the principal axis of symmetry Cn is symmetric, meaning positive 1, then this particular IR will be termed as A, and if it is negative 1, then it will be termed as B. So, for symmetric character with respect to Cn is A, while antisymmetric character with respect to Cn will be as termed as B. So, next we look at the characteristic of the irreducible representations with respect to the perpendicular C2s with perpendicular to the principal axis of symmetry. So, if the characters of the representations which are one dimensional, if the characters are with respect to the C2 primes are symmetric, that means plus 1, then they will be given subscript 1. If it is antisymmetric, then a subscript 2 will be given. Okay. So, once we have designated whether it will be A or B, then we have to look at the behavior of the characters with respect to the perpendicular C2s. If it is symmetric with respect to perpendicular C2, meaning if the character of character is plus 1 corresponding to C2 prime, then it is A1 or B1. Otherwise, if it is the character is minus 1 with respect to C2 prime, then it is A2 or B2. in case there are no C2 primes, then one has to look at the characters corresponding to the vertical plane of symmetry, and we will follow the same trend. So with respect to sigma v, if the character is +1, then the subscript 1 will be used. If it is antisymmetric, that is -1, then subscript 2 will be used. And in many cases, primes and double primes are attached. So primes and double primes are attached to all these letters A, B, or E when appropriate to indicate those which are respectively symmetric and antisymmetric with respect to sigma h. Okay, so if the character correspond to sigma h is positive, then you have a prime. If it is negative, you will have a double prime. In certain cases, we will have point groups with inversion symmetry as one of the symmetry elements present. So in those cases, particularly, we look at the characters for this inversion operation, and if the character is symmetric, that is +1, then we will have subscript G with respect to the terms like A, B, or E, and if it is antisymmetric, that is -1, then I will have subscript as U. Okay, so this G and U are coming from the German word gerade, ungerade. Okay, so apart from this, these are the most commonly used symbols for irreducible representations. But other than this, there are certain numerical subscripts that are used for the symbols E and T, but we will not discuss those things right here, and for most of our purpose, those will not be very much required. Next, we look at the area 3. So area 3, if you look at, what do we have? We have 6 different symbols. Okay, so let's have a look at area 3. So this is the region I'm talking about. So we have total 6 symbols: 1, 2, 3, 4, 5, 6. So x, y, z and rx, ry, rz. X, y, z are the Cartesian coordinates, and these r's are the rotational symmetries with respect to each axis, which is given as the subscript. So about x axis, if the rotation is there, then I have rx, otherwise ry or rz. Fine. So you will find that these are the only 6 symbols that you have in area 3 always in all of the character tables. Now their positions, they will be placed against certain irreducible representations. So that will depend on the particular property of the irreducible representation corresponding to that particular point group. Those we will discuss in detail at a later stage. Okay. As we said that any algebraic function can act as the basis function, and we can form any basis set out of those functions, and we can use any vector also, like I talked about the bond vectors. So we showed earlier the examples with taking x, y, z for say example C2V point group. Now we are discussing with respect to one particular point group here, C3V, for this particular character table. So now if I consider that C3V point group, the matrices for one operation each from the 3 classes that we can have 3 classes for C3V, as we know. So then we can get the matrix is as follows. So this is corresponding to E, C3 and sigma V. Okay. So now here what we can see is that this character in this case, in this matrices, the z is always separated from x and y. So z never mixes with x and y, but x and y they mix, because you cannot get any particular one-dimensional representation for x or for y, but you can get it for z. X and y always transform together. Okay, so they always transform together to form a representation. So that's why when we form this matrix representation, if you remember, then we form for xy and separately z, and altogether we put all xyz and get this 3 by 3 matrix. So here we can see that C3 mixes of x and y to give x prime and y prime. So x and y jointly form a representation. Hence it is equivalent to observing that the 3 matrices are block factored in the same way. So I can think about that. Okay, so you can see this is a block and this is another block, right? So here also I can think about that I have a same block, same way. Okay, so here and here. So I have 3 matrices block factored in the very same way. So therefore we can form 2 sub matrices if I consider those 2 blocks individually, and I get one representation for just z alone, while I get another representation where x and y transform together. Okay, so we get 2 by 2 matrices. So from here what we can conclude is that this gamma z is the A1 irreducible representation. If you just go back and see the character table, then you will find that it reality is that this gamma z is nothing but the A1 reducible representation, while gamma xy is the E irreducible representation. Okay, so and you cannot separate this x and y contributions. Okay, now let's look at the area 4. So area 4 also you will see certain functions which are like binary products of x, y and z. So it may be either x y, x z, y z, or x square, y square, z square, and so on. So this pair of functions, they must have the transformation property, the same transformation properties as a pair x y, since z goes into itself under all symmetry operations in the group. Okay, so this binary functions x y, x z, or x square, y square, they form basis for certain irreducible representations, and this part will be more clear when we deal with certain properties or observations like Raman spectroscopy and all. Okay, so we will stop here, and in the next class we will talk more about these irreducible representations and look at their properties by learning this so-called great orthogonality theorem. Thank you very much for your attention. See you tomorrow.